Hello everyone and welcome back to the implementation session of day 3. So far we have covered quite a journey. On day 1 we understood what are the differences between artificial intelligence, the machine learning and deep learning. We also looked into the neural networks. We also saw how features and labels make up a dataset. We also looked into what are the training and testing phases of data. We even built our first machine learning model using linear regression. Then on the second day, we moved deeper into the mathematics behind the deep learning, where we discussed different functions such as vectors, matrices, activation functions, loss functions, gradient descent, and after all, the optimization. Now today, we are finally going to connect all these pieces together. Today is the day where we build our first actual deep learning model. Until now, we have been discussing the concepts. Today, the machine starts. Let's ask ourselves a simple question. Why can't we just use linear regression model everywhere? Remember our students' marks prediction project that worked because the relationship was simple. More study hours generally meant more marks. A straight line could represent that relationship. But what if we want to recognize the faces? What if we have to detect cancer from medical scans? What about translation languages? Generating text like ChatGPT. A straight line is never enough. Real world problems are complex, and that's where neural networks come in. Neural networks can learn highly complex patterns, and for that, we need to import a library which is TensorFlow. Now, let's begin by importing the library. As discussed earlier, TensorFlow is Google's deep learning framework. Think of TensorFlow as a toolkit that helps us build and train neural networks. Whenever we see modern AI applications, there's a very good chance TensorFlow or PyTorch is running behind the scenes. Then we will be creating our first neural net. So first, let us start with implementing our TensorFlow, including our TensorFlow and other important libraries. So for that, let's take a text box and write importing libraries. And this we'll have to insert a code which is import the main libraries such as NumPy as np, import pandas as pd, import matplotlib as plt. Then we also need to import from sklearn.model selection. We need to import testing and training split. Then we need to import from sklearn.preprocessing. We need to import standard scaler. Then from sklearn matrix, import accuracy score. And finally, import TensorFlow as TF. So whenever I'll be typing TF, that means I am calling up to the library of TensorFlow. Now let us see or move on how to insert or import the data. For that, we need to type here a new code which will talk about importing the data. Now for this particular example, we are importing Indian diabetes data because India is also known as diabetes capital, and diabetes data in India will be of very large sort and from which we will be able to derive few outcomes or few predictions as well. So for that, I'll have to write URL equals to, I'll have to paste a particular URL for that. I've copied my URL. and this URL should necessarily be presented in double inverted commas so that the machine can understand that. And after that, we also have to write the column names that the URL has. So let us first go to that particular URL. I hope my screen is visible to you right now. So this is the PIMA's diabetes dataset, and these data are presented in a form. Now I know the form of these datasets, columns. So I'll write column names, column underscore names equals to, and in that, first of all, I'll have to write pregnancies. Then I'll have to write about glucose content. Then the blood pressure. Then the skin thickness. Then insulin. The body mass index or the BMI. Then the pedigree function. Now by this, I have written all the related column names and I have imported the URL as well. So for this, I'll now be running this particular cell to get it. Okay, the cell has completely been executed without any errors. So next thing I'll have to do is, first of all, I'll have to check whether the dataset has been imported correctly or not. So for that, print, and in print I'll be looking at first 5 rows, and first 5 rows are presented as df dot head. They're presented as df dot head. Then we also need to check the shape of the data. So for that, let us do this. Df dot shape. When I run this, it is going to print us our first 5 rows. The first row is going to be about pregnancies, second is glucose, then blood pressure, skin thickness, BMI, insulin, and it goes on and on up till the outcomes. So the last thing that we wrote about was outcome, starting from pregnancies, glucose, blood pressure, skin thickness, and all. And there are total 768 data points that are present in this particular data set, divided over 9 columns, that are the nine columns, right? The pregnancy, glucose, blood pressure, and all these are known as the features, and the outcome, whether the person has diabetes or not, that will be presented in the column that is the outcomes. So now we will have to start feature engineering as well. For that, I'll add a code here, code line. Just mention here that we are starting with feature and labels Okay, I'll start writing about the, first of all, we will write about the x-axis, that is x equals from x. First of all, I don't want this particular thing, that is the outcomes. So I'll write that particular thing down. df dot drop. I'll have to remove the column of outcomes. Outcome, and I'll have to set axis to 1, axis equals 1. Okay, then I'll have to present about y as well. Y equals df dot drop. For y, I'll have to present df, that is the outcomes. So I'll have to write here outcome. Okay, now I'll have to print the shape of x and the shape of y as well. So for that, print, in print I'll write x, feature shape, and that will be presented as comma x dot shape, and the similar thing will go on for y as well. So that will be presented as, instead of feature, I'll have to write label. L-A-B-L-E, label, and instead of X we'll have Y. Control enter. So this will show feature shape as 768, 8 and label shape is 768. So 768 data points in each of them. The features, that we have 8 features and we have one row or one column for the outcomes. That is the outcomes, that is the output that we want. Now we will move on with the feature scaling. So let us write about that thing, the feature scaling. Okay, we will write in this one only. So this will be scalar equals standard scalar, and we will set it. Okay, and x equals, we will scalar fit on x, scalar dot fit underscore transform, and we have to transform x, only x. So what exactly do we understand by scalar fitting? So when we do this scalar fitting, we have to make sure that the model is fitting correctly. If the model is not fitting correctly, we won't be able to understand what is happening beneath the model that we are testing. So for that, we'll have to run this particular code. So the code has been executed. Now the next thing that we have to do is about splitting the data into one part into the training and the another part into testing. So as we did in earlier examples as well, we will set 80-20 type of, we will do 80-20 type of distribution. 80% will go for training data set and the 20% will go for testing. So for that we will have to write the code. First of all, we will add the text, that is train test split. Okay, train test split. And in this we will have to add the code block for x underscore train, then we have x underscore test, then we have y underscore train, and we have y underscore test. So this is the function that we are defining, and inside this definition we have to write about train test split. And for this function we will have to specify x, then we will have to specify y, and we will have to specify the test size, test underscore size. Now test size, as we said, we have to define it to 0.2, we have to define it to 0.2, and after this we'll have to set random, we'll have to set random states, random underscore state to 42. Okay, so when I click on run execute, it will execute completely. Now we'll have to print the length of training and testing datasets. So we'll have to print in bracket, I'll have to write training x, and in this I'll write length of x underscore train. Okay, x underscore train, and I'll copy this, I'll paste it right here, testing, and instead of x train I'll write here x test. Now I'll copy these both lines and do it the same way for y. Instead of x, I'll just be printing here y. So x train becomes y train and x test becomes y test. When I control enter, it is going to print me that 614 data points will be used for training and 154 will be used for testing purposes. Now becomes the real part. Until now we were performing simple things that were similar to that of machine learning, or introducing or making a simple neural networks. Now we will start building the deep learning model, and for that we need to add the next line of code in which we will be writing about model that is equal to tf.keras tf.sequential, and in this I'll be specifying the first thing, which is the first network I am building, the first dense layer that I am building, tf.keras.layers.dense. Okay, and in this I'll be writing about the first network in which I am going to take 32 neurons. So single, as we understood earlier in the first session, the neurons are similar to what work in our brains. So here as well, the neurons, the more the neurons, more number of relationships the deep learning network is going to finalize. It is going to come up with complex and integrate relationships from the data that we have provided. Then we are also going to imply an activation function. Activation equals ReLU. ReLU necessarily stands for rectified linear unit. So here in rectified linear unit, what happens is, for example, if the data is having zero value, so instead of just showing a zero value or null value or any other value, it is the data is going to just be set to zero. This provides, or a negative value is going to be set to zero. This provides that whether there is a linearly growing graph, the linearly growing graph, as we discussed in our first session, similar to more the number of hours of study, the more marks we are going to get. So that graph was a linear graph. Instead, in the real life situations, we don't know what are linear things and what are non-linear things. So to mimic that, we introduce the ReLU function in which the negative things are barred at zero. This provides some kind of non-linearity, and by that non-linearity, we can understand or predict the upcoming events. So for that, we need activation function, which is ReLU, and then we also need input shape. Input underscore shape equals to 8 comma 8 comma. So why did we write 8 comma? Nothing else. So this 8 is necessarily the 8 features that we are going to classify. Which are the 8 features? Pregnancy, glucose, blood pressure, skin thickness, insulin, BMI, diabetes degree function, and age. So these are the 8 features that we are going to classify our output upon. Now this was the first layer that we built. Now we also have to build another layer, which will have tf dot keras dot dense, the same thing here. So I'll just copy it from here and paste it here. So that becomes dense, and in dense I'll be writing there will be 16 neurons again, and same, we need activation equals to ReLU okay. And similarly we will add one more layer, but here we will need one neuron and activation. Let's say instead of ReLU, I suppose sigmoid. So what is sigmoid activation function? So instead of ReLU, we are going to use another activation function, which is sigmoid, which will take the exponential part of the data that we are giving it or feeding it. So layer 2 is going to combine the layer 1 with the new meaningful patterns, and the third layer is going to combine the layers 1, 2, and 3 with the new intricate patterns that it is going to come up with. Exactly how our human brain functions. The final outcome is one output neuron, the final decision, one prediction. For now, we will keep it simple. Now we will move on to compilation. So what a model compilation is, it is the most important step while making a deep learning model. So students can just memorize this line, in which we are going to use Adam optimizer, and we are going to use an MSE or mean square error loss function. So let us see how it is done. So for that, I'll input a text and I'll write here. Okay, run this particular thing. There seems to be an error. Okay, tf dot seems I forgot a comma here, comma, and here as well a comma. Control enter. Yeah, it's done now. Now here I'll have to write model compilation. Now these are few easy lines of codes that the students can memorize as well. So we will just have to write model dot compile, and in compile we will have to write optimizer equals to adam or adam, anything is fine. And then we will have to write the loss function. Loss is equal to binary cross entropy, binary underscore cross entropy, comma, binary cross entropy. Then matrix, metrics, matrix is going to be the accuracy. Accuracy. Okay, we'll just try to run this. Yeah, the model compilation works, and then we are going to print the model summary, what kinds of functions it has applied on itself, and what optimizers it has replicated with, and what are the loss functions. All these details will be provided in the model summary. So now print, and in print I'll write about model summary. Okay, model summary, and in this I'll have to write model dot summary. Enter. So this is the model summary that we are going to use. We have used one layer which was about 32 neurons, second layer was 60 neurons, and the last layer was about 1 neuron only. So these are the 288 parameters that were used in the first layer, 528 in the second layer, and only 17 in the last layer. So there are total of 833 parameters. Trainable were 833 and non-trainable were 0. So all the parameters that we have passed, all the parameters are going to be trained. Now we are going to move on with the training of model. So for that I'll have to write history. History, that is of model fitting, model dot fit, model fit, and in this I'll write x underscore train, x train, then y train, x train, y train, and this is going to run on total of 20 epochs. Epochs equals 20. Then I am going to have validation split. Validation split for 0.2, that is 20%. And last but not the least is the verbose, was 1. Now until this runs, let me tell you what this particularly understands. So first of all, let us know what the Adam optimizer was. So Adam is one of the most popular what we say optimization algorithms. Similar to what we learned about gradient descent yesterday, Adam is improved version of gradient descent. It automatically adjusts the learning rates and usually performs well. Whenever we are unsure, Adam is to be used. Then we looked at the model parameter. Then this particular single line that we are doing here, it says history is broken. Okay. Okay, instead of cross entropy, let us write about MSE. Let us run this and let us run this again. Yeah, it is running on epochs. Also, all the epochs will be covered, all the 20. This will show the accuracy of each and every epoch. So first of all, it was 66%, then it became 67%, then it became 70%, and the accuracy rises and goes on rising until it reaches 80%. So final accuracy that we have got is of 80%. The loss that we have suffered the first in the first epoch was 22%, and final loss that we have suffered is 13%. And the validation accuracy 73% we have got finally, and validation loss is 15% only. So this is about uh, the training and splitting of data basically. Now what we have to do is these inputs are trained on 8 different features as we told, like age, the blood pressure, glucose level, BMI and all. Whereas the Y is giving us the answer. This is the label. Y is the label what we want to predict, whether the person has diabetes or he does not have diabetes. Then in the epochs, this epoch section, it means that one complete pass through the data set. Suppose we have 1000 records and one epoch means the model sees all 1000 records at once. This means the 20 epochs means the model sees all the records 20 times. Each time it improves its internal weights. Now, what happened during training? During each epoch, first of all, the model is going to make some predictions. It is going to calculate the errors. Then it will gradually arrange the gradients. And then it will update the weights as well. This thing, everything is going to repeat itself. This is known as backpropagation, which is the heart of deep learning. We see things, we learn things. Then we apply the same things again. Then we see them again, then we apply them again. And this cycle continues. Similar thing is happening with the neurons which are present in the deep learning model that we have made. Okay, now let's solve a real healthcare problem, which is about diabetes. Can we predict whether a patient has diabetes or not? This is extremely important problem. Early detections can save life. Hospitals worldwide use this predictive analysis for the similar tasks only. And for this, we have used this particular Pima dataset. Now we are going to move on with model evaluation. So let us move on with evaluation. I'll write a text about evaluation and adding a line of code here. Loss, comma, accuracy equals model dot evaluate x underscore test. Okay, let me check here. X underscore test, and we need y underscore test as well, y underscore test. Okay, now we need to print accuracy. So print, and this in this we need to write accuracy, and the accuracy is going to be represented by, okay, so by this we can understand the basics of accuracy. Control and enter. So accuracy comes out to be 75%, that is 75.32%. Now we will be moving on with predictions. And for that I'll need a new line of code. So a new line of code, predictions equals model dot predict and x underscore test, then predictions equals, if predictions are greater than 0.5, that is 50%. Predictions are supposed to be greater than 50%. Then we also need accuracy. So for that, okay, 0.5. For that we need to write about accuracy. ACC equals accuracy underscore score, and this will be defined as y underscore test comma predictions, y underscore tests comma predictions, and that is going to print our accuracy score comma ACC. So the accuracy score that we have got is 75.32 again. Now we will be moving on to plots, all the figure and plotting graphs. So the main graph that we have to draw is accuracy graph. Okay, accuracy graph. And in accuracy graph, I'll write, first of all, I'll be starting with the figure size. So plt dot figure, and in this I'll have to write fig size equals 8,5. Then I'll have to write plt dot plot. We'll have to plot the historical graph, that is the about the this part, which part, this particular part, this part, this part, model fitting part. So for that we'll have to write here history dot history, and in this there is one thing, accuracy, and label is going to be training accuracy. Label is going to be training accuracy. Now we will also have to plot another graph which is about the validation accuracy. So let us write it in this only, plt.plot. I'll just copy this particular thing and write it, copy it over here, and here instead of accuracy I'll have to write validation accuracy. Okay, and it will be labeled as validation accuracy, and for this I'll have to write down plt.title as model accuracy, model accuracy. Okay, and plt.xlabel is going to be epoch. It is going to be epoch, and same occurs on the last one as well, plt.ylabel. It is going to be accuracy, and we also need to draw the legend, plt.legend, legend, and we also need to plot the grids, or no, it is fine if we don't plot the grids. Okay, now plt.show. Now this is going to show us the plot or the graph that we are working on. Okay, so this shows certain accuracy. Okay, we need a comma here, we need a comma here as well. Okay, when we run it again, going to give me epoch. Okay, is the problem here. Okay, instead of x label, let us write here x label, and instead of y label, rerunning. Yeah, we have our training and validation accuracies. Yeah, okay, and the upper one is the training accuracy, the lower one is the validation accuracy. So these are the two accuracies. Now we will also be looking at the graphs for the loss functions. So let us copy this particular thing only. Okay, Control A and Control C. I'll move on to the next line, which will be about loss functions graph. So here, let us do some changes. History of loss, training loss, validation accuracy. So instead of validation accuracy, I'll have to write validation loss. Okay, now moving on to the next, model accuracy. Instead of model accuracy, okay, we don't have, I guess, validation loss, okay, model accuracy. So instead of this, we need loss. Epoch and accuracy. Instead of accuracy, we need loss. Control and enter. So this is going to give us the model loss diagram or chart. As we can see, over the period of epochs, the loss is minimizing itself. So now that we have this data, can we test it on a new patient? So the answer to this is yes, we can. Let us check on sample patient. Sample patient, PATIENT, sample patient. Okay, new code line, and in this new code line, I'll write about new patient, new underscore patient. Let us write him as np.array. Okay, np.array, and in this we will form few arrays. The first one is going to be about pregnancy. Let us take 0 pregnancies. Then glucose, let's say 120. Then let us take blood pressure as 72. Let us take skin thickness as 20. Then the insulin level 79. BMI 25. Then diabetes 0.5 and age 33. Okay, now we will have to provide the same things on the new patient. Transform the scales. For that, new underscore patient, PATIENT patient equals scalar dot transform, and in this I'll have to write new patient. And for prediction, I'll have to move this thing into prediction equals model dot predict, and for him as well, new patient, new patient. And lastly, we'll have to write about print prediction probability. In this, we'll have to write about prediction beginning with 0 and 0. Now, if the prediction is greater than 0.5, that person is diabetic. If it is not, he is non-diabetic. So let us write it in code as well. If prediction 0, 0, so this thing, if this thing is greater than 0.5, print patient is diabetic. And else we have to print the patient is non-diabetic. Okay, so let's test him. Okay, so prediction probability is 13% and the patient is probably non-diabetic. So yeah, that completes with our third day, I guess. Yes. And in this we have seen about regression versus classification. Regression is what happens when we are predicting numbers. Examples of regression patterns include house pricing or temperature or weather analysis, then salary identification or regression. Then we have another thing of categories, which is classification, in which we predict the categories, like if the emails are spam or not, if the person has cancer or not, if the person is diabetic or not. If these kinds of model are yes or no type of model known as classification models. Now, suppose we have tested 100 patients and the model accuracy predicts, let's say, 90%. That means that our model is 90% accurate, and validation works on the same thing as well. Today, we build a real neural network used in multiple hidden layers. Applied ReLU activation function used Adam optimizer, learned about the loss function, and performed trainings using epochs. We also understand what classification problems are and started solving a real world healthcare problem using an AI. This is a major milestone because from today onwards, you are no longer just learning AI, you are building artificial intelligence systems. Excellent work, everyone. Today's session marks the transition from basic machine learning projects to actual deep learning. In the coming sessions, we will move even further and start working with the images in convolutional neural networks or computer vision and intelligent applications which are going to power many modern technologies. If you enjoyed today's session, do leave your doubts and questions in the comment section. If this lecture helped you understand your deep learning better, please like the video, share it with your friends and classmates, and subscribe to my YouTube channel. Also remember to visit Ingiverse, where you will find complete course recordings, practice materials, the quizzes, certificates, and additional technical resources. And if you are interested in learning beyond AI, check out my major playlists on Sahil at Work YouTube channel, which includes works on algorithms and problem solvings, data science using Python, microcontrollers and microprocessors, and other signal processing things as well. Until then, keep learning, keep building, and most importantly, stay curious. I will see you in the next session. Adios.